Hello, I'm Soumyadeep, a second-year graduate student in the astronomy department at Caltech, working with Professor Sri Kulkarni. And today I'm going to talk about my recent work, which has uncovered a variety of variable stars residing in such beautiful-looking planetary nebulae. I will discuss how we found those systems and also give highlights on some of the most interesting sources in our sample. A bit of background first. So planetary nebulae are short-lived end states of low-mass stars with masses between 1 and 8 solar masses. These stars start off as a main sequence star, like our sun, and then ascend up the giant branches, at the end of which the core starts to contract, forming white dwarfs, and the envelope gets ejected. The newborn white dwarf is very hot with temperatures of 100,000 Kelvin, and it ionizes these ejected envelopes, creating these glowing planetary nebulae, with the white dwarf being the central star of the planetary nebula. But this is for single star, but things can become very complex pretty quickly in a binary or multiple star system. For example, in a binary, the giant can completely engulf its companion, creating something called a common envelope, which results in a planetary nebula, but with a closed binary sitting inside, where the two stars, one being the white dwarf, is orbiting around each other with a period of a few hours to a few days. There are also theories to avoid the common envelope totally, which creates a planetary nebula, but with a wide binary inside, where the period now is a few months to a few years. And there can be 10 other ways the two stars can interact. And these weird interactions are what create such amazing shapes of planetary nebula, which are far from any spherically symmetric shape that only single star evolution can create. More direct evidence of binarity inside planetary nebula came from the study of light curves in the last century. So light curves show us how the flux from a source varies as a function of time. In a case of periodic systems like this one, we see a periodic signal in the light curve, as shown in this figure, where the period here corresponds to the binary orbital period. So this is an example of a variable light curve, which is also periodic. But there can be other ways a light curve can be variable. For example, there can be outbursts, there can be eclipses, and there need not be a period. So the question we asked is, are there any other kinds of variables that we can find and learn new phenomena? This led us to our work with this amazing machine in town, this Wiki Transient facility, which scans the whole northern sky, creating light curves for billions of sources. But for our work, we only focus on the central stars of planetary nebulae. We generated their light curves, but most of the stars are not actually variable, and we are looking for a few variable needles in a haystack of non-variable light curves. But fortunately, we have amazing magnets to pull out those needles. And these magnets are variability matrix, which are statistical matrix quantifying the amount of variability in a light curve. In my work, I use this normalized excess variance matrix and also von Neumann statistics and Pearson's Q matrix spaces to pick out these variable stars. I will skip the details, but please feel free to contact me or read my papers if you are interested to know more about them. The result of this search was the discovery of a whole variety of variables. Firstly, we discovered several short period post-common envelope binaries with light curve periods of a few hours to a few days. But the remaining bit was extraordinary because we found all these different kinds of variables, such as this object, which shows these dips, objects showing outburst, or sources which are varying over the whole ZTF baseline of 6 years. For example, this one, or these objects which are varying over timescales of months. So we have a whole sample of sources which we can start following up and try to decipher what these systems are doing, and some of them can teach us new phenomena or new physics. I will now give some highlights on some of the most interesting sources. I will go back to this object whose image I showed in the first slide, which is WESB-1. This is the same image where we can see the beautiful planetary nebula, and this is the central star. This image was taken with the Isaac Newton telescope in Spain as a part of their work on this object. In this figure, there are a lot of light curves from different instruments and different wavelengths, but we can just focus on the ZTF light curve. The y-axis shows the relative flux, and the x-axis is days. The remarkable aspect of this light curve is these eclipses. And sometimes these occultations are going all the way up to 100% of the flux. And we do not see any period in this light curve, which led us to conclude that this is a transiting debris system where there is a debris disk made up of asteroids or planet-like material. And each of these asteroid is creating its own eclipse, resulting in this final light curve. This is an interesting discovery because this is one of the first detections of debris disk inside planetary nebula, and the first one to show these clear occultations over several years. We also quickly realized that this is not a single star system, but a wide binary, which can be seen clearly in this spectral energy distribution, which is flux as a function of wavelength. The optical wavelengths is dominated by the cool star, which has a temperature of around 6,500 Kelvin and radius of 6 solar radius. So it is a subgiant-like star. But the signature of the very hot white dwarf can be clearly seen in the ultraviolet. So this is a hot white dwarf and a subgiant wide binary. We also see significant infrared excess, which tells us that there is a lot of dust, which is emitting in the infrared, being heated up by the hot white dwarf. I will now change flavor to talk about some of the long timescale variable objects. This is one of the most interesting system among them, which is NGC 6833, which shows a 980-day periodic signal with the ZTF R and I bands, which are the redder bands, showing these triangular-shaped brightening events, which is also seen in the infrared light curves by WISE, the space mission. But the amazing thing about this light curve is that the ZTF-G band shows a dip instead. At the same time, the redder bands shows these brightenings. We do not have a consistent explanation yet, but the stability of the period strongly indicates that this is a binary object, with the binary period being 980 days. This will make it the fourth longest known periodic binary inside a planetary nebula. We also have more wide binary candidates with periods of 700 days and 230 days. I should mention here that these wide binaries are interesting discoveries because these are very rare systems inside planetary nebula. And this is one of the power of ZTF with its long baseline of 6 years, that it is being able to discover these long timescale variables and long period binaries. We also have these objects which are evolving over the whole ZTF timescale without any period. These two objects have doubled their brightness over the whole ZTF baseline, which is also seen in the WISE light curves. A spectroscopy study of this particular object shows that this is one of the youngest post-AGB star known, and we think that this can be a late thermal pulse object where the very young white dwarf has started to reignite some of the fuel in its core and is going back to a giant phase. And this is what it's doing. It's going back to a giant phase. So in summary, we have uncovered a wide variety of photometrically variable central stars of planetary nebulae and made several interesting discoveries. For example, this debris disk system or wide binary candidates, or even more exotic systems like late thermal pulse objects. We have also demonstrated the success of variability matrix to efficiently find variable objects from a pool of light curves. With that, I will end my presentation. Thank you.